Good morning. All right, today we're going to start the last full chapter of the semester. This is chapter 5, and this is one. There are two sections in chapter 6. It's section 1 and section 6, but they go together. In chapter 5, we're going to deal with something called logarithmic and exponential equations, or functions. And then chapter 6 is systems of equations. It's a continuation of what we did in chapter 1. So, to begin with, let's review chapter 2, section 3. Composite functions. Composite simply means one and another. It's a function within it. With composite functions, it's a function within a function. All right. What you will hear a lot of times, people take college algebra, you'll hear people talk about the Fogg and Goff method. This is how we represent composite functions. Yeah, I could have, this is a function within a function. The way this is expanded, because what this says is in the function f, anywhere you see an x, put the function g. That's what that means. This is f. The way you read this is f of g of x, which is now, see why they call it Fogg. It's f of g. That's what they call Fogg. And likewise, this is g of f, because it's the function g with respect to the function f. So what does that mean? Let's say we had two functions. Because with these functions, whatever's inside the parentheses is the variable inside the equation. Whatever is the variable is inside that first parenthesis. So if I put a capital M in there, that means anywhere I see an X, I put a capital M in its place. That's how you read that. So if I had f of g of x, that means in the function f, which is this one, anywhere I see an x, I put a g of x. So it would be 3 g of x plus 2. That's what that equation looks like. Because in place of x, I put g of x. Then what is g of x? G of x is x plus 4. Get rid of the parentheses. And combine like terms. So that is our composite function g, f of g. So this is our Fogg. So what would that one look like? Well, it's g of x. This is the word of. So it's g of x. So it's g of x. That means anywhere I see a G inside here, I put what G of X is. Now, what this means is in my function G, anywhere I see an X, I put X plus 4. That's what X is, plus 4. Get rid of the parentheses. So my GOG is X plus 8. That's how you do it. All right, so let's look at our examples. This is chapter 2, section 3. Because we need to know these so we can we start chapter 5. So example 1, given f of x is that, g of x is that, find all 4 of these. Example 1. So f of x is 2x minus 5. G of x is x squared minus 3x plus 8. Find the fog, and then also find the GOF. What the first one means is f of g. So it's f of g of x. And the second one is g of f. So it's g of f of x. On the left side, since g is inside the parentheses, so this equation goes anywhere you see an x in the outer function. This equation goes in place of x. So it's 2 times x squared minus 3x plus 8. That's the 2x. Then we have a minus 5. Get rid of the parentheses. 2x squared, positive, negative is negative. 2 times 3 is 6. Positive, positive. 2 times 8 is 16. Minus 5. Combine like terms. So 16 minus 5 is a positive 11. So that is my fog. And the second one, since the f of x is inside the parentheses, that means I take this equation and inside the g, anywhere I see an x, I put that equation, 2x minus 5. Because this is my g of x. Anywhere I see an x, I put the f of x. You could look at it this way. Here's my function g. So anywhere I see an x, I put an f of x. That's just this. My variable used to be x. Now I change it to f of x. This is f of x. So anywhere I see an x, I put an f of x. What is f of x? 2x minus 5 squared. 3 times 2x minus 5 plus 8. Now, this one means 2x minus 5 times 2x minus 5 minus 3, 2x minus 5 plus 8. We got to multiply these two together. We got to multiply these together, and then we can combine everything. 2x times 2x is 4x squared. Positive and negative is negative. 2 times 5 is 10x. Negative and positive is negative. 5 times 2 is 10x. Negative and negative is a positive. 5 times 5 is 25. That takes care of that. Now, negative times positive is negative. 3 times 2 is 6x. Negative and negative is a positive. 3 times 5 is 15. Plus 8. So that's that. That's that one. And there's that. Whenever you get rid of parentheses, always combine like terms. So how many x squares do we have? We only have the first one, 4x squared. Now the x's, 10 minus 10x minus 10x is minus 20x. Minus 6 is minus 26x. So that takes care of those. Now the constants. Notice we go from x squared to x to the first to no x's. 25 plus 15 is 40, plus 8 is 48. And there's our answer. So that's how the Foggin-Goff works. Let's look at what B says. Now, what B is saying is let's find the fog when x is 7 and the Goff when x is 7. Now, let's look what this really means. This means f of g of 7. And this one means g of f of 7. So what we do first is let's find what g of 7 is. G is x squared minus 3x plus 8. And since 7 is inside the parentheses, anywhere I see an x, I put a 7. Seven squared is 49. Negative and positive negative. 3 times 7 is 21. Plus 8. 49 minus 21 is 28. 28 plus 8 is 36. So that's f of g of 7. Likewise, now the next one. F of 7, f is 2x minus 5. So anywhere I see an x, I put a 7. 2 times 7 is 14. 14 minus 5 is 9. So f of 7 is 9. Oops, nope. I didn't finish yet. This is just g of 7. I just did inside there. Now I got to take, this is my g of 7. 36 is my g of 7. I got to find f of g of 7. So this is my, because the f of g of 7 is 36. And f is 2x minus 5. So it's 2 times 36 minus 5. So f of g of 7 is 67. So here we found f of 7, which is 9. So that is not what we put inside the g. Because this is that. G is x squared minus 3x plus 8. Anywhere I see an x, I put a 9. Nine squared is 9 times 9 is 81. Negative times positive is negative. 3 times 9 is 27. Plus 8. 81 plus 8 is 89. Minus 27 is 62. So that's my value for g of f of 7. Yeah, it's just plug and play. We first have to find f of 7. Once we find f of 7, whatever that value is, we put into the g. Find the g of 7, whatever that is, put in. We can do it that way. That's a short way. Or we can plug it in here. Since we're looking for f of g of 7, we can just plug it in here. F of g of 7. Once we did the f of g part, it's 2 times 7 squared minus 6 times 7. 2 times 49. 6 times 7 is 42. 2 times 49 is 98. 98 minus 42 is 56. 56 plus 11 is 67, which is exactly what we got down here. Same thing, we can put it in this one. Since this is the g of f, we want g of f of 7, we put in there. So it's 4 times 7 squared, 26 times 7. Yeah, so this one's going to be 4 times 49 minus 42, 182. 49 times 4 is 196 minus 182 plus 48. 196 minus 182 is 14. Plus 48 is 62, which is what we got. So you can pick the way you want to do it yourself. So that's example 1. Let's take example 2. Given that f of x equals the square root of x and g of x equals x minus 3, find Fogg and Goff and the domains. So let's find Fogg. F of g of x. This is f of g of x. So anywhere I see an x inside the f function, I put g of x. So here's an x, I put g of x. That's what that says. Now g of x is x minus 3. That's what g of x is. So there's the Fogg equation. Its domain Remember, in square roots, you cannot have negatives. You can have zero. So the smallest this equation can be is, if we set it equal to 0, it's a horizontal shift 3 to the right. So my domain is 3 to infinity. Do the same thing with the Goff. Of f of x. That means inside my g of x, anywhere I see an x, I put an f. So I have f of x minus 3. F of x is square root of x. So this is a Goff. All right, so let's draw the graph like we did in chapter 1 or chapter 2 at transformations. So the main function is the square root of x. The graph looks like that. There's no horizontal shift. There's just a vertical shift. It goes down 3. So there's my new origin. My origin shifts from there to there. So the domain is x is greater than or equal to 0. Because all it did was a vertical shift. Again, the faster you memorize the charts, the library of functions, the easier all this stuff is. Example 3. Given that f of x equals 1 over x minus 2, and g of x is 5 over x, find Fogg and Goff. So this is f of g of x. This is g of f of x. All right, so the first one, f of g of x. In my function f, anywhere I see an x, I put a g of x. So I put a g of x there. What is g of x? G of x is 5 over x. So it's a fraction minus a fraction. We have to get a common denominator, which is x. So I have to multiply this one by x over x. 5 over x minus 2x over x. We fixed the bottom. Now the top is a fraction also. It's 1 over 1. So with these, take the top fraction, leave it alone, and multiply by the flip of the bottom. And multiply those together. And there's our equation. I just plug it in there, simplify. Fraction over fraction, take the top, leave it alone, flip the bottom. Now, the only domain problem we have here is the bottom cannot equal 0. So we got to find out what makes the bottom equal to 0. So 5 equals 2x. X equals 5 over 2. So that's the only number we cannot have. Our domain is x cannot equal 5 over 2. It could be anything else. It cannot equal that because you cannot have zeros on the bottom. I'm going too fast, tell me, because this is just review a lot of all the rules we've done all semester. Again, yeah, that's why I went over the first part of the semester. I went over a lot of fractions, because that's just it. Whenever you have a fraction over a fraction, take the top fraction, leave it alone, and multiply by the bottom, flip of the bottom. That's the conversion. So it used to be C over D, now it's D over C. That's what I did here. Yeah, until here, I treated both top and bottom separately. The top is 1, the bottom is this fraction, 5x minus 2. Have to combine these two, get a common denominator. So again, it's all the rules of order of operations. Well, this one says, inside the g function, anywhere I see an x, put an f of x. So inside my g, anywhere I see an x, I put an f of x. F of x is 1 over x minus 2. So this is a fraction over a fraction. Take the top fraction, leave it alone. Multiply it by the flip of the bottom. And multiply. The bottom is 1, so nothing happens. 5x minus 10. The domain, since this is a linear equation, domain is from negative infinity to positive infinity. Because we learned in chapter 1, the domain of a linear function is always infinity. So that's how you create composite functions. A function inside another function. Let's go backwards now. Let us decompose our functions. Decomposing a function. What this means is if I have f of g of x, can I break it up into its individual equations? For example, let's say our function h of x was x plus 2 squared. Is this a function within a function? Yeah. Inside here, you have an equation. So that's the g of x. So here you have g of x squared. That means the f of x must be x squared. Because it's whatever I have my function squared. So f of g of x would be anywhere I see an x, I put a g in its place. And g of x is the internal x plus 2. So here's g of x. It is x plus 2 squared. That's the hardest part, is finding what part is the inner, what part's the outer. H of x is equal to 1 over x plus 3 squared. We could look at this two ways. One way we can look at that is our f of x is 1 over x squared. And our inner equation, g of x, is x plus 3. because this is my original one. I have 1 over x squared. So if I pull this out, that's my g of x. What I really have left is 1 over x squared. And this has to be my f of x. So f of g of x. Here's f. Anywhere I see an x, I put a g of x. And g of x is x plus 3 squared, which is what we started off with. That's one way you could do it. Another way we could have done it is f of x is 1 over x. And g of x is x plus 3 squared. So when I do my composite function, f of g of x, in my f function, anywhere I see an x, I put a g. What is g? X plus 3 squared, which is what we had to begin with. So again, either one of those will work. As long as we could, when we do the composite functions, it gets the same thing. So that's the tricky part. Let's look at example 4. H of x is equal to 2x minus 3 to the 5th. Find f of x and g of x. So what is f of x? What we want is a composite function of f of g of x. So what is the f of x is the outer. It's the outer equation. This is the inner. So which one's the outer? Yep, very good. And the inner? Perfect. That's all there's to it. Very good. Example 5. H of x is equal to 1 over x plus 3 cubed. We want f of g of x. So we want f to be the outer and g to be the inner. So what is f? X cubed. Yeah. And g of x? Very good. That's simple. So that does it with, so that's composite functions. That's all we need to know in chapter 2, section 3. Because now we're going to start using those. Let me stop here.